Um recadinho inicial, já está posto no chat. A professora Sandra estará operando para os participantes que tiverem interesse na declaração de participação do evento. A professora Sandra estará operando para os participantes. É só enviarem nome completo e CPF para o e-mail do colégio, colégio@unidave.edu.br, ok? Olá, hello. Assim cumprimentamos a todos nesse final de tarde aqui do sul do Brasil, em Santa Catarina, Rio do Sul. Cumprimentamos a todos que nos prestigiam no lançamento do livro, A Tabela Periódica, uma breve introdução. Cumprimentamos especialmente o professor Eric Serri e o professor Marcos Eduardo, que nos presenteiam com as suas participações neste evento. É uma honra tê-los conosco. Hello, so we greet you all in this early evening from south of Brazil, Santa Catarina, Rio do Sul. We greet everyone who honors us at the launch of the book, The Periodic Table, a very short introduction. We welcome especially Professor Eric Serri and Professor Marcos Eduardo, who give us their participation in this event. It's an honor to have you both with us. Welcome. It's a great pleasure for me to introduce our speakers today, Professor Eric Serri and Professor Marcos Eduardo. Professor doutor Eric Serri, autor da obra, químico, escritor, filósofo da ciência, autoridade mundial sobre história e filosofia da tabela periódica, autor e editor de vários livros nesta área e áreas afins. Professor Eric Serri, author of the book, chemist, writer, philosopher of science, a world authority on the history and philosophy of the periodic table, and the author of several books in these and related fields. Professor doutor Marcos Eduardo, dos membros do comitê científico da obra traduzida, que reuniu pesquisadores e professores da área de química de todo o Brasil e atual presidente da SBEC, Sociedade Brasileira do Ensino de Química, professor de Química, atua no ensino médio desde 1987 e no ensino superior desde 2017. Professor do Instituto Federal Sul-Rio-Grandense. Professor Marcos Eduardo, one of the scientific committee members of the book, translated into Portuguese that brought together researchers and chemistry teachers from all over Brazil. He is the president of Brazilian Chemical Society of Teaching. He teaches chemistry for high school since 1987 and higher education since 2017. He teaches at Instituto Federal Sul-Rio-Grandense. Neste final de tarde aqui, início de tarde na Califórnia, Los Angeles, neste tempo que agora, presente, ainda que horários diferentes, nos conectamos, nos encontramos neste momento duplamente histórico para o lançamento do livro. A Tabela Periódica, uma breve introdução. O primeiro livro traduzido, publicado pela editora Unidave, e o primeiro livro traduzido para a língua portuguesa do autor Eric Serri. And so, how did everything begin? Então, como tudo começou? 2019 era o ano internacional da tabela periódica promulgado pela ONU. Nós, enquanto colégio, olhamos para essas comemorações e entendemos a sua importância e de que precisaríamos trazê-la à tona. Então, pensou-se a partir do grupo de iniciação científica estudantil, JEIC, do qual participantes, estudantes do 6º ao 9º ano do ensino fundamental e ensino médio. Nós nos debruçamos e começamos a planejar ações que trouxessem reflexões acerca da tabela periódica para o cotidiano das pessoas. Entre as ações, delineou-se um projeto de articulação entre ciência e arte, onde a arte comunicava as informações da tabela periódica por meio de 6 personagens que eram elementos químicos: Para tanto, criou-se a rainha hidrogênia, seus ministros oxigênio e hélio, e seus operários praseomídio, estrôncio, rubídio. Essas intervenções artísticas comunicavam a presença dos elementos químicos em elementos, fenômenos do dia a dia, das pessoas, naturais e não naturais. Essas intervenções aconteceram ao longo de todo o ano, envolvendo toda a comunidade escolar, institucional e extra-institucional, uma vez que ela acontecia nas áreas comuns, por vezes na recepção central, por vezes eram nos corredores, por vezes nos estacionamentos. Foram 4 grandes intervenções, com intervenções menores, intercaladas ao longo do ano letivo. Uma outra ação foi a elaboração de experimentos pelos estudantes do GEIC, posteriormente desenvolvidos com os alunos da educação infantil da época e o ensino fundamental anos iniciais. Então, os estudantes pesquisadores do GEIC identificaram experimentos que apresentassem os elementos da tabela periódica no cotidiano das pessoas e levaram para as turmas de educação infantil e para as turmas do 1º ao 5º ano. Uma terceira ação que se delineou foi a aproximação com o professor Eric Serri, que tem um trabalho notável no que diz respeito à química e à história e filosofia da química. O fato das professoras que estavam envolvidas no GEIC naquele momento terem tido a oportunidade de conhecê-lo em 2014, em um evento em Foz do Iguaçu, veio à tona a ideia de conversar com ele sobre o que estava se estudando, de ver o que nós poderíamos fazer e até promover a sua vinda, de estar com os estudantes. Então, os estudantes do GEIC entraram em contato com o professor Eric Serri via e-mail. Muito felizes, recebemos a sua resposta disposta ao diálogo. Desse diálogo, dele com os estudantes de iniciação científica, surge a possibilidade de nós traduzirmos uma de suas obras para a língua portuguesa pela primeira vez. Estando nós em um espaço privilegiado e contando com a presença de uma editora, do entendimento de gestores da época de que seria um grande feito para o ensino da química, tanto a nível estudantil quanto acadêmico e formação de professores, o projeto foi acolhido. A editora, na sua pessoa de responsabilidade, a jornalista Sônia, também acolheu o projeto. E, por fim, chegaram até mim, professora de inglês destes estudantes. Chegaram até mim, através da professora doutora Sandra, propondo a tradução do livro. E assim foi que também abracei esse projeto. Abracei esse projeto que foi acompanhado pela professora Sandra em todas as etapas da tradução deste livro. Foi uma honra poder colaborar nesse projeto, que hoje é ampliado para mais um idioma, a língua portuguesa. Chegou a me emocionar, gente. Esse é um projeto que nasceu do diálogo de estudantes com o pesquisador-autor e que acabou afetando gestores, professores, representantes de diferentes setores da instituição que entenderam a importância desse feito, que culmina hoje no lançamento do livro. É com alegria que compartilhamos como chegamos até aqui, com o coração agradecido a todos os envolvidos na tradução deste livro para a língua portuguesa. Muito obrigada. E agora, ouviremos o professor Eric, que fará uma breve apresentação sobre os assuntos que estão abordados na obra. Questões que continuam abertas, em desenvolvimento, que continuam sendo discutidas. O professor Eric fará sua fala em inglês. Ao final, faremos um apanhado geral sobre suas colocações. E depois ainda, o diálogo entre o professor Eric e o professor Marcos, e eu espero colaborar de alguma forma. And now, we are going to listen to Professor Eric Serri. After his presentation, me and Professor Marcos will present briefly in Portuguese. After that, Professor Eric and Professor Marcos will talk about a few topics, and I hope to be able to help you both. So, sintam-se à vontade para conversar, dialogar. Professor Eric, Professor Marcos, Eduardo, feel comfortable to talk. So, welcome, Professor Eric.
Thank you, Claudia. Thank you very much. I'm very, very happy to be here. I've been to Brazil twice. I love Brazilian culture. I love Brazilian football. I love everything about Brazil. So it's a special pleasure for me that this book has been translated into Portuguese. It's, as Claudia mentioned, I think it's the first of my books to be translated into Portuguese. I hope there will be more in the future. This book is a little bit special because it's addressed to a general audience, and it's addressed to students and teachers and professors, and it's a small book, so it doesn't require too much effort for a person to understand, read this book, and hopefully make use of it in teaching in an original way, in a new way. So I'm going to make a presentation in a moment. So for me, that's probably enough for now. And I look forward to this dialogue with Professor Marcos. So over to you, Professor Marcos.
Professor Marcos.
Oi. Qual é a questão, Cláudia?
You can say hi, hello.
Hi, Professor. I'm glad to meet you. I read your book, first in English, and now the translated by Claudia. And soon I will have some questions about the testing, about the periodic table and all.
Okay, so now, Eric, the presentation is yours. Feel free, and you both feel comfortable to talk when you want. So, aqueles que estão assistindo aí, o professor Eric fará sua apresentação, e vocês que nos assistem, nos presenteiam com as suas presenças aí, sintam-se à vontade também para escrever no chat, dizendo de onde vocês estão, ou até algum recadinho sobre a importância da química, como a química tem afetado a tua vida, se você para nós tem sido uma honra poder estar lançando esse livro, e temos a certeza de que ele não é, como o professor Eric disse, não é um livro muito grosso, só nós podemos ler, é um livro de uma linguagem simples, né? E que é possível para os nossos alunos de ensino médio, nível de ensino superior e sim de formação de professores. Então agora é com você, Eric Serri. So, Eric, it's your turn.
Okay. So will you, good. Thank you. So can the screen be made a little, perfect.
Yeah, good.
Thank you, Claudia. All right, so this is just a picture of my own institution, UCLA, University of California, Los Angeles. And here are some of the books I've written. The one in question is this one, the third one in this periodic table of books. Okay, if we could have the next slide, please.
Okay.
And this, of course, is the book that we're here to talk about. And I'm going to be saying this many times, but let me say it even at the beginning. I want to thank very much Claudia for having made this translation.
My pleasure.
Next slide, please. And I want to thank other people. I want to thank Sandra Aparecida dos Santos, Annalisa Grunfeld de Luca, Marcos Ribeiro, Nadia dos Santos, Valdemir Neto. I hope Valdemir is here. I've known Valdemir for many years. For a conference together that he organized. And many other people who were involved in the making of this translation and the making of this book. Next slide, please. So, I begin by making a very quick history of the periodic table. The book begins by discussing the Greek views of the elements. And as you know, the Greek philosophers believed that there were initially 4 elements that corresponded to these shapes, the Platonic solids. And then when a 5th solid was discovered, they decided that there should be a 5th element, the quintessence. Now I'm going to jump 2,000 years or more to Lavoisier, the famous French chemist. He is the one who defined elements in the modern way that we understand elements, the element as the last stage of decomposition. If you take any chemical compound and you break it down, as you know, you reach a stage when you cannot separate anything anymore. This is, according to Lavoisier, an element. John Dalton, who comes next in my pictures, he made a connection between elements and atoms. He appealed to the ancient Greek idea of atoms, but he made it more quantitative. Here is a list of the atomic weights for each element, according to Dalton. You can see hydrogen. It's very small, I know, but you can hopefully see that hydrogen is 1 and oxygen 7, phosphorus 9, etc. This was the first time the weights of atoms were compared with each other. This idea led to the notion of triads, which are illustrated on this periodic table I show here. For example, there is lithium, sodium, and potassium in the very first column on this side, in group 1. And I'm sure you know what a triad is. We have 3 elements, of which the middle element is the average of the flanking elements. So sodium has the average atomic weight. So if you take lithium and you add to potassium and you divide by 2, you get approximately the value for sodium. With atomic numbers, this relationship is exact because we're now dealing with protons, which are a whole number. And these triads are everywhere on the periodic table. You can see in blue in the S block, in brown in the P block, and in green in the D block, etc. Okay, if we could have the next slide, please. Now, the discovery of the periodic table is usually attributed to the Russian chemist Mendeleev. And of course, he is the most important of the discoverers. But it's important to realize that this is an example of multiple discovery. The discovery was made independently by at least six individuals. In France, Bégayer de Champcourtois produced the periodic table that you see below the French flag. It's a 3-dimensional periodic table. The first periodic table was already 3-dimensional. Then we had Newlands in England. Then we had the Danish Heinrichs, who was living in the United States. His periodic table is shown below the Danish flag. And Odling in England, and Lothar in Germany. It's a simultaneous discovery, although it took about 7 or 8 years, but they were working independently. Next slide, please. And now, Mendeleev is the most important discoverer, yes, but he is the 6th and final discoverer. He was, of course, Russian. What distinguishes his periodic tables and his discovery was that he left, as you know, empty spaces for elements that had not yet been discovered. And even more than that, he predicted the atomic weights for these elements. For instance, you can see 44, 68, and 72. I show them with red asterisks. And also 100. These elements were discovered eventually. And they had almost exactly the atomic weights that Mendeleev predicted. 44 is scandium. 68 is gallium. 72 is germanium. Almost exactly correct. And this is why most sources, most books will say that it's Mendeleev who was the discoverer. Right. I and many historians of chemistry disagree a little bit. It's a multiple discovery. If we could have the next slide, please. Moving historically, the periodic table, of course, is explained these days in terms of electron configurations. The configurations shown here are the original ones due to Bohr in 1913, in which he used the old quantum theory. He used just one quantum number. An electron was either in the first shell or the second shell or the third shell. That's it, simple, one quantum number. And already he was able to say lithium is like sodium and like potassium because they all have a one outer electron. If I could have the next slide, please. Now, when quantum mechanics was developed between the years 1924 and 1926, the theory became much more solid, much more fundamental. And this is due to Pauli, Heisenberg, Schrödinger, de Broglie, Fermi in Italy, Dirac in England, Born in Germany. It's again, multiple components of the discovery were made. Yes, please, Claudia. Now, when quantum mechanics was developed, it became clear that we needed not just one, but 4 quantum numbers that I'm sure you're all familiar with. N, L, M subscript L, etc. Now it became possible to explain that the first shell would have 2 electrons, the second shell would have 8, the next would have 18, etc. Next slide, please. Moving historically even more to current days, the discovery of the last 4 elements, or the most recent 4, then we don't think that it's the last one, are these elements: nihonium, moscovium, tennessine, organeson. And here are their atomic numbers shown. The scientists are currently working to try and create or synthesize elements 119 and 120. Next slide, please. Now, that was a very quick overview of the history of the periodic table from the Greek philosophers of 3,000 years ago to modern times. But today, in this presentation, I want to talk about something else. Something that is discussed in the book, but these are the open questions, the remaining questions. Right? The periodic table is not a closed book. It's still a developing story. And I want to specialize now to concentrate on these more specific topics. Yes, please. As I was saying, quantum mechanics explains the periodic table, as every student of chemistry knows. The groups of elements in columns are in columns because they have the same number of outer shell electrons. Okay. Now, does quantum mechanics explain everything about the periodic table? Is it a closed book? Is it a finished theory? I'm going to show you that it is not. Next slide, please. Now, the slide seems to have got a little bit messed up because of sending it. Never mind. According to what I was saying in the blue table on the left of this slide, the first shell is 2, the next shell is 8, the next shell is 18. If we use that information, we would predict that the closing of the shells should take place at numbers 2, 10, 28, 60, etc. In fact, the closing of the shells takes place at 2, 10, 18, 36, the noble gases. So why is there a difference? Next slide, please. Okay, the difference is because the shells don't fill one after the other. They don't fill sequentially. They fill diagonally in the way shown in this diagram, which is sometimes called the Madelung rule, the N+L rule. And again, I'm sure that all students and teachers of chemistry use this rule and know this rule. Next slide, please. Now, this rule, interestingly, is known by different names in different countries. I don't know what the name is in Brazil. I know that in Mexico, it is known as the diagonal rule, and it was due to this man, Keller Torres. They're sometimes called the Madelung rule or the Janet rule. In French, or in France, it is known as the Kleczkowski rule. Kleczkowski was a Russian, but in France, this is it. So many, many names, but it's the same rule. Okay, so next slide, please. So here it is, N+L. What is the explanation from quantum mechanics of the N+L rule? In 1969 was the 100th anniversary of the periodic table. And in a famous Swedish chemist called Lövdin made this statement: it is perhaps remarkable that in quantum theory, the simple Madelung rule, meaning N+L, has not yet been derived from quantum mechanics, from first principles. Okay, next slide, please. We are now 50 years after that. It still has not been derived from first principles. Many chemists and physicists and mathematicians have tried to explain this rule from quantum mechanics. So it's not a closed book. There are still important questions, such as how to derive the N+L rule. Quantum mechanics does not explain everything about the periodic table. Next, please. So the Lövdin challenge, as it's known, still exists, still stands. The periodic table is not fully explained by quantum mechanics. Next, please. Now, another area which is of active research in these days is what's called relativistic quantum mechanics. Because when the atomic number of an element gets very high, relativity theory from Einstein, from physics, makes changes so that it is possible that elements do not behave in the way that they should behave according to which columns they are in the periodic table. Next slide, please, Claudia. For example, the color of gold, the element gold, is now explained as being a relativistic effect. To say it briefly, when a particle travels at a very high velocity, changes occur according to the theory of relativity. For example, the inner electrons are contracted. The inner orbit shrinks, gets closer to the nucleus, and consequently, the chemical properties of the element changes. And it has been discovered that the color of gold, which is almost the only element which is not of a silvery appearance like mercury, or most of the metals, as you know, are silvery. Gold is not. The reason is relativity theory. Mm-hmm. The fact that mercury is a liquid and not a solid like most other metals is also now explained according to the theory of relativity, the special theory of Einstein. Next slide, please. Now, if you take a look at this slide, I have highlighted two heavy elements, Rutherfordium, Rf, dubnium, Db. When these elements were first studied, when their chemical properties were studied, it was found that they didn't behave in the way that they should. Dubnium should be like tantalum and niobium. But in fact, dubnium behaves more like protactinium, Pa. Rutherfordium, Rf, should behave like hafnium and like zirconium, but it doesn't. It behaves more like plutonium, which is somewhere else on the periodic table. Okay, so this makes it look like when the atomic number gets very large, the periodic table loses its validity. It breaks down in some way. Next, please, Claudia. But the situation is even more complicated. When chemists and physicists first discovered the element 107, borium, they found that it did behave in the same way as rhenium and technetium. Right? It forms a compound, metal O3Cl. And so there was an article in Nature magazine entitled Boring Borium, to mean business as usual, no problem, no funny business going on. Similarly, that's okay. Let's go to, that's fine, that's perfectly okay. The element 112, which is even heavier, again, behaves in the way we would expect it to behave. If you look at this graph, these are the enthalpies of sublimation of elements: zinc, cadmium, mercury, copernicium, 112. It's an almost perfectly straight line. Copernicium does behave in the way that it should. So there's now a kind of a confusion. How important is relativity theory? If it's important for Rutherfordium and dubnium, why is it not important in copernicium and borium? Thank you, Claudia. If we could have the next slide. I wrote an article in Scientific American, and the title given actually by the editors of Scientific American, I didn't choose this title, was Cracks in the Periodic Table. And you can see the diagram. It's as if the periodic table is breaking down. This is a bit of an exaggeration. The periodic table is not finished. It's not broken. But it gives the idea of what is beginning to happen in some of the very heavy elements. Thank you. The next slide, please. Okay, question. Is there such a thing as an optimal or best periodic table? Next slide, please. I'm going to talk to you about a table that I discuss in the book, which may be the best possible periodic table. And this is how we arrive at this best periodic table. You take the element helium from its usual position, and we move it to the top of group 2, as shown by that arrow moving like this. Okay. Secondly, if we could go to the next slide. Now we have helium in the top of group 2. We make a cut, and we cut the S block, and we move the S block to the right-hand side of the periodic table. Next slide, please. And we arrived at what's called the left step periodic table, shown at the top here. Now, as you can see, this is a very regular shape compared to the traditional periodic table shown below. But it's not just that it's a regular shape. If you look at the traditional periodic table, you see something a little anomalous, a little strange. The first period is 2, then 8, 8, then 18, 18, 32, 32. The first period of 2 does not repeat. But in the left step periodic table, the first period of 2 does repeat. It's more regular. And if we believe that there is a fundamental explanation of the periodic table in physics and in electronic configurations, this may be a superior periodic table. But there's a lot of debate among the experts. Also, this table shows, going back to the N+L rule at the top left-hand corner, every period is a value of N+L. First period, hydrogen, helium. Second period, lithium, beryllium, etc. So there are many people who believe that this is a superior periodic table than the traditional one. Next slide, please. Now, one disadvantage, or to some people's mind, a disadvantage. If we can go back one, Claudia, if you don't mind. I just want to make a, okay. If you look, thank you. If you look again at the left step periodic table, helium is being placed among some really quite reactive metals like beryllium, magnesium, calcium. This sounds strange in a chemical sense because helium is completely unreactive. But as you see on the next slide, it's not completely unreactive. There is a compound of helium that was formed in 2017, Na2 helium. Okay, of course, this was made at very high pressure. This doesn't exist at atmospheric pressure, but it does show that helium is not completely unreactive. If we could have the next slide, please. Now, when I say the optimal periodic table, maybe it's not quite the right word. Maybe we should say the most fundamental table, the most philosophical table, or the table that is showing closest agreement with the Madelung or N+L rule. Next slide, please. Now, let me move to another topic, which is debated in current times. Group 3 of the periodic table sometimes appears, as I show on the left, scandium, yttrium, lanthanum, actinium, and sometimes you see it on periodic tables, scandium, yttrium, lutetium, lawrencium. Now, my students come to me, thank you, good, and the same thing here, okay? On the top one, scandium, yttrium, lanthanum, actinium. On the one below,
Sorry.
okay, on the one below, scandium, yttrium, lutetium, lawrencium. So students are confused. They want to know which is correct, right? Perfectly legitimate question. Which is correct? So now there's a lot of research being conducted to try and resolve this question. If we could see the next slide, please. According to chemical and physical properties, it turns out that it's impossible to choose one or other. If you look at some properties, it points to one group 3. If you look at other properties, it points to another version of group 3. Similarly, electronic configurations cannot resolve this question. Okay, if we could have the next slide, please. Now, I have proposed a simple way to resolve this, which does not depend on electronic configuration or does not depend on chemical or physical properties. First of all, show the periodic table in its long form, 32 columns, as shown here. Secondly, insist on all the atomic numbers increasing one by one in regular order. Okay, 2 very simple, very modest demands, requirements. If we could have the next slide, please.
Sorry, okay.
Okay, so if you insist on putting lanthanum and actinium in group 3, as in the top table, you see a problem. Okay, the problem is that the numbers do not increase sequentially in order. You have number 70, number 71, and now 57, and then 72. And in the next period, 102, 103, 89, 104. But if you put lutetium and lawrencium in those positions, everything works perfectly. 70, 71, 72, 102, 103, 104. Okay? So on that argument, it looks like the second option is more correct. But things are always more complicated. If you look at the next slide, please, you can see that there is a third way of doing this, which preserves lanthanum and actinium in group 3, okay? And it preserves the increase in atomic number everywhere, but it requires splitting or dividing the D block into a very uncomfortable division. First, one column of D block, group 3, then a big gap, and then 9 groups, titanium group, the vanadium group, and so on. Right? So this feels, to some people, for instance me, this feels uncomfortable. This feels wrong. Why should the D block be split? We don't split the P block. We don't split the F block. Why just one block to be split? So to me, this feels like an unnatural periodic table. So I would reject this option. Next slide, please. And maybe try again, because there may be something more on this slide. Okay, good. Now there is actually a fourth possibility. Number 4, the UPAC periodic table. Strangely enough, UPAC does not take a position on the question of group 3. If you look closely at group 3, scandium, yttrium, nothing and nothing. And the F block now becomes 15 elements wide, not 14, but 15. And that causes problems to some people, because the F block is about 7 F orbitals, 7 times 2 is 14. So this doesn't seem to agree with quantum mechanics. So we have 4 possibilities. I recommend number 2. Okay, we do not split the D block, as in number 3. We have 14 elements in each period of the F block. All the elements follow each other in sequential number. Okay, next slide, please. Now, UPAC set up a commission, set up a working group, and I'm actually the chairperson of this group, to investigate this question. If you can see the date, this was started in 2015. So it's been 6 years. This has not yet been resolved. There are still complications and arguments. But I think, or I hope, UPAC will eventually settle on option number 2, as I showed you earlier. Next slide, please. Now, I'm coming to the end of this presentation. And as I said earlier, I love football. I very much admire Brazilian football. And as you can see, this is a periodic table of football in which you may be able to recognize some players. For instance, I don't have a pointer, so I can't point. But I can point, because I can talk about elements. P for Pelé. S, Socrates. Rn in the noble gases. Ronaldinho. And next to Ronaldinho, I don't know. What is this AT? I don't know who that is. Does anybody know who AT is here? No.
Marcos, do you know?
Yeah, of course. I have my preference. And magnesium.
But who is AT? And then,
você sabe que é o que está do Ronaldinho?
Qual que, Cláudia? De um corte.
Você sabe quem está do lado do Ronaldinho?
Deixa eu abrir uma imagem um pouquinho maior aqui, que aí está muito pequenininho para enxergar. Um pouquinho.
This is Ronaldo, the real Ronaldo, the Brazilian Ronaldo.
O Ronaldo é.
Yes, I think so.
I don't know the players. I usually don't watch soccer, so I can't help.
Beryllium is Bebeto.
Yeah.
Bebeto? Yeah, I think so.
And potassium, K, is Kaká. And next to him is Cafu. And so on. I would love to be able to name all the players. So if anyone listening and watching can help me, I got this periodic table from the internet, and it had no information. So I've been trying for many years. This was produced in 2009. I've been trying for many years to identify as many players as possible. By the way, borium, mentioned in my presentation, number 107, is Beckham, BH, the British player, the English player. F for fluorine. Who is this? Figo from Portugal. And Maradona is MA in the F block, etc., etc. Okay, that's the end of my presentation. There is one more slide, which is another very important periodic table of desserts. Thank you very much for listening. This is my website if you want to see more information. I would be happy to answer questions either from Marcus or from any of the audience. And thank you very much for listening. It's been a pleasure.
Thank you, Professor Eric, for sharing all this knowledge. And I was very happy because I could follow and understand everything. I guess I'm talking about a translator, not someone who is the expert on this issue, but I really had appreciate that. So, Professor Marcos, gostaria de fazer aí um apanhado geral para nós sobre aquilo que o professor Eric Serri acabou de apresentar para nós. E eu acredito, então, que nós temos um desafio aí, que é aquele que sabe aí nomear esses jogadores aí. Está o endereço aí do professor Eric e vamos completar essa tabela, né, pessoal? Então, vamos lá. Professor Marcos, com você.
Então, eu não conheço todos os que estão ali, mas os meus preferidos... Professor Serri, my idols ali, Magnésio e Rênio, Mauro Galvão e Renato, the players, né? I have my club in Brazil called Grêmio, né? Em Porto Alegre, né? E the shirt blue, white and black, né? Magnésio e Rênio are the elements with these players. Bom, Cláudia, então, eu faço um comentário geral sobre a fala.
Sim. Então, o livro, ele descreve, né, a história, que ela parte ali dos elementos gregos, né, vamos ali para ele conta toda essa história que começa ali, chegamos até as tríades, então passamos por todos esses colaboradores, e é isso, a gente gostaria de ouvir de você, professor Marcos, um resumo, né, aquilo que o professor Eric acabou de falar, e depois a gente vai para as perguntas, então.
Tá certo, tá bom. A fala do professor Serri vem na ideia da construção da tabela periódica. Primeiro, um movimento histórico, né? O professor, ele anda nesse barco da história da ciência, da filosofia da ciência. Então, ele traz um apanhado desde o começo da ideia da tabela periódica, quando se pensava em associar elementos químicos de uma forma ou de outra. As construções que foram sendo feitas ao longo desse tempo culminam, né, com uma ideia de formato da tabela periódica como nós a conhecemos já há algumas décadas, né? Entretanto, a fala do professor Serri vai ao encontro de propor uma modificação na distribuição dos elementos a partir da inclusão dos elementos que estão no bloco F e que são colocados na parte inferior da tabela, incluindo-os no bloco, dentro do bloco, né? Separando o bloco S, onde estão ali os metais, né? Do bloco D, que inicia lá, então, pelo escândio e pelo ítrio. A discussão que ele traz é onde vão, ou qual é a posição adequada aí para lantânio e actínio, ou então depois lá para lutécio e laurêncio, né? Ocupando as posições que vão abaixo, então, do escândio e do ítrio, né? A ideia dele é inserir os elementos desse bloco F lá no bloco central, de maneira, então, aí, a alargar um pouco mais a tabela. Essa é a ideia que ele traz ali. Ao longo da fala do professor Serra, ele traz ainda outras discussões que provocam uma compreensão que se precisa desenvolver, né? E provoca, de fato, uma nova discussão, né? Algumas delas eu vou trazer depois, aqui nas perguntas, que, por exemplo, sobre o hidrogênio, sobre o hélio, onde é que o hélio está colocado, né? De que maneira esses elementos vão estar lá, por que o hidrogênio, que não é um metal, está colocado no grupo de metais, né? Por que o hélio, com a sua configuração eletrônica, está colocado dentro de um grupo onde os demais elementos químicos têm outra configuração diferente dele? Então, são discussões que ainda podem acontecer em função do formato da tabela periódica e ainda exigem novas contribuições de outros pesquisadores ao longo desse tempo. Então, ele reconhece que grupos de cientistas ainda continuam pensando no formato, continuam pensando na alocação de alguns elementos, e que eu chamo aqui de um instrumento vivo, ele chama de livro aberto, né? Tabela que ainda é um material, um instrumento ainda em construção, ainda em desenvolvimento, e que tem ainda alguma coisa a evoluir. Resumindo, Cláudia, as palavras do professor CRM foram nesse sentido.
Isso aí, lembrando sim que ele a tabela periódica, ela é aberta, né? Se eu posso falar isso, né? Essa história ainda continua e o nosso tempo corre, né, gente? E para isso nós temos aqui ainda uma pergunta que foi inclusive enviada pelo professor Marcos. So, Professor Eric, we have one question which was asked by Marcos, by the way, that qual é o limite da tabela periódica na forma como a conhecemos? Até onde ela pode ser ampliada? So, what is the limit of the periodic table? How far can it be expanded?
Okay. Well, there are many different views on this question, as I'm sure he knows. One estimate is 172. And this is calculated from relativity theory.
Okay.
There are some people who think it can be even higher. But speaking more realistically, it is already extremely difficult to produce elements, let's say 117 and 118. As you know, they become less and less stable. When they form for a nanosecond or 3 nanoseconds. And so it looks like we have already reached almost the end of the periodic table. So in my opinion, even though the relativity experts say 172, I don't think it's going to get as far as that. I think maybe 120, 125. But that's just my opinion. I have no way of being sure about that. We will have to wait and see. Nobody really knows.
So we are almost there, yes? Ok. Marcos, gostarias de...
No, Professor, I will speak in Portuguese, if you don't mind, and Cláudio will translate, ok? Uma última frase, né? No Brasil, a tabela periódica é usada por estudantes a partir dos 14 anos, né? Durante todo o ensino médio, chamam de high school, né? cada série escolar se usam algumas características da tabela. Ok. A tabela é um instrumento que representa a ciência viva, né? A ciência em movimento, né? O professor diz que ela é um livro aberto, né? Isso é pergunta 3 lá embaixo da Cláudia. A sua forma, a quantidade de elementos, né? E mesmo a posição de algum elemento podem ser modificados de acordo com as compreensões, né? Eu gostaria, embora ele tenha falado isso, embora o livro tenha essa discussão, mas para quem não leu o livro, né, eu gostaria de falar um pouquinho sobre um elemento que eu julgo encantador, que é o hidrogênio, pela sua estrutura, pela sua forma de disposição das partículas, né, o hidrogênio, né. A sua organização interna é peculiar. O seu posicionamento no grupo 1, como ele falou, pode causar conflito com a compreensão da estrutura dos metais, e mesmo nas ligações químicas, né? Então, como é a compreensão do professor, né, sobre a posição adequada para o hidrogênio, deslocando ele dali, colocando em outro grupo, ou criando uma situação especial para ele? Cláudia.
Okay, so in Brazil, in high school, students start using the periodic table at school when studying. And so I'm going to summarize Marco's question, right? And so his question is about the hydrogen. Yes, I don't know if I if I pronounced it correctly now. So even it is in this book, if we can see, so it's on page 169. So, para aqueles que estão assistindo, está aqui descrito a posição do professor a partir da página 169. So, the question is, what is the right place to this element, in your opinion? Like few words.
I think the right place is in group 1, because of its one outer electron. I know that in some tables it is sometimes placed in group 17 because it forms a diatomic molecule. I also considered that possibility, and in the first edition of the book that has been translated, I made that argument. But now, because of the reactions of some readers, because I thought about it some more, I'm going back to the traditional position of hydrogen. Group 1.
Ok, thank you very much. Então, o grupo, ok, professor Marcos, é o grupo 1, de acordo com o professor Eric. E mais alguma pergunta?
Não, acho que estou satisfeito. Não sei se no chat tem alguma questão de algum colega.
One more, if
Tem
I
alguma
can add
questão?
one more thing. Hydrogen is not a metal. And so it seems strange that we should put it in that group.
Yes,
But in many groups, the first member is anomalous. The first member of most groups, right, is different, is strange. Oxygen is a gas. The other members of that group are not, etc. And so there's nothing too much to worry about with hydrogen. Yes, it's not metallic.
Good.
That's okay.
Good, very good. Não há muito que se preocupar, então.
Convém, eu acho que traduzir essa frase dele, né, que ele está dizendo que em vários grupos da tabela periódica, o elemento inicial de cada grupo também tem uma diferença em relação aos demais, né? Ele cita, por exemplo, o oxigênio, no grupo 16, que é um gás, né? E os demais elementos abaixo dele, a partir do enxofre, são sólidos. Então, o primeiro elemento de cada grupo também teria uma diferença em relação aos demais. Então, não seria uma peculiaridade nem do hidrogênio e nem do hélio lá no grupo 18, que também, por ter só 2 elétrons, e no grupo que tem todo mundo com 8, também tem uma variação nesse sentido. Thank you, professor.
Ok? So, let's end. Ok? Aquisições do livro. Onde você poderá adquirir o livro? na livraria da Unidade, Central Livros. O WhatsApp é 479-8424-5644. Eu já iria começar a falar os números aqui do telefone em inglês. I started to say the numbers, the phone number in English, so that's it. So, também estará sendo posto no chat, né? Ok? As informações. Nós iremos finalizar tomando emprestado as considerações da professora Annelise, do professor Marcos, a professora Annelise, que o professor Eric também já conhece, professor Annelise, you met in Foz do Iguaçu. So, nós vamos tomar emprestado o que eles escreveram no prefácio da segunda edição e que também está na contracapa do livro, que diz: a tabela periódica é uma das principais descobertas da ciência. Sua observação sempre causa algum sentimento que pode ser de admiração e fascínio, até espanto e aversão. O fato é que aproxima e aglutina informações que podem ser usadas por diversas áreas do conhecimento, o que a torna um instrumento interdisciplinar. O percurso histórico apresentado neste livro promove uma viagem científica, conhecendo as ideias e os entendimentos de diversos pesquisadores, em seus tempos, espaços e culturas, mostrando que alguns conhecimentos permaneceram e outros sofreram rupturas. Os conceitos científicos discutidos são apresentados no contexto e importância, entendendo a tabela periódica como um instrumento interdisciplinar que possibilita explicações sobre fenômenos químicos, físicos, biológicos, enfim, da vida. Tenham um bom final de tarde, tenham um bom final de dia. Professor Eric, have a good afternoon there. Thank you very much. It was a pleasure, an honor to have you here. Professor Marcos Eduardo, have a good evening. Thank you very much for being with us and sharing all this information, knowledge that has changed a lot our lives, okay? So,
tchau, obrigado.
Bye,
Boa
bye.
noite a todos. Boa noite, professor.